The one with the t-shirt with fuck off with Ethan on it. You can put it on YouTube.
It is on YouTube. Live streaming starting now. Okay. Start. Okay, so welcome to the seminar today. We're starting after summer break. To start, we have the summer students to see what they have done during this month. We have three presentations today, and the first one is the one by Labib Asari, who has been working with Mohammed, with the Google Fellow, correct? On GPUs in Gnuastro. So, Labib, whenever you want, you can start.
Okay, sure.
Someone is connecting and has the micro, or maybe it's me.
So should I start?
Yeah.
Well, hello everyone. I'll be giving a presentation today about how I was working on integrating GPU support in Gnuastro. So a little introduction about me. I am a third year computer science student at VJTI Mumbai. I've been studying subjects like operating system, database management systems, computer networks, and computer architecture as part of my bachelor's. My major interest lies in the field of machine learning and deep learning, where I'm used to processing big amounts of data for doing various intelligence tasks. I also have some experience in backend web development. I worked with GNU Astro as part of Google Summer of Code program this year. So Google Summer of Code is an initiative taken by Google to promote open source contributions among students. So every year, GNU Astro takes parts in Google Summer of Code and selects a few students. So luckily, I was selected this year. I worked on creating a Python library for GNU Astro as part of my GSOC. And the next thing I work on was adding the GPU support inside the GNU Astro library. So this is what I will be talking about today. So before understanding why we need GPUs in GNU Astro, let's first understand how the existing GNU Astro executes. So the existing GNU Astro uses normal CPUs for execution. So we must first understand how the normal CPUs works, what are the problems with it, and what are the potential solutions, and how do GPUs help us. So let's see, how does a normal computer work? So computers seem very magical, but because they can like do anything that we want them to do, like we can browse anything on the internet, we can play games, we can play videos on it, we can do any sort of mathematical analysis on it. So they seem very magical, they can do anything. But if we break it down into smaller components, one by one layer of abstraction at a time, if we go at a very low level, everything that a computer does is extremely logical. Every instruction that it executes is basically a logical representation of an instruction set that a computer actually understands. And those instructions are extremely simple. So in a general computer, there are two most important things. The first one is the central processing unit. This is the one responsible for actually executing the instructions. The second is the memory of the computer. This is where all of the data about your application is stored. So say when I launch my browser to do any task, it first loads the browser, like whatever application data which is there in my browser, it first loads it from the long-term memory which is stored in my hard drive. It first loads it into the main memory. The main memory is where all the applications that are currently running or executing, all of the data and instructions of those applications are present in the main memory. And then the CPU fetches one instruction at a time and then decides what data this instruction is supposed to be executed on. And then it fetches the instructions and the data, and then whatever the result is, it writes it back to the memory. And this continues until as long as we are executing the as long as we are running the application. So let's understand what the CPU is, because this is essentially what currently Gnuastro uses to execute all of its programs. So the CPU is, as I mentioned, the main brain of the computer. It is responsible for doing everything that we are trying to do on the computer. So all of the applications that we try to run, all of the softwares that we run, all of the things that we do, all of the memory management and hardware management, all of this is done by the CPU. And CPUs also have a speed at which they can operate. So even though the current modern CPUs have evolved a lot and they seem to be doing a lot of things at the same time, but still internally they have a limit at which they can operate. So this limit essentially means they have a certain number of operations that they can execute in a single second. So for modern CPUs, those number is very large. It's in millions to billions. So that means that a CPU can execute millions to billions operations per second. So the next part of the computers is the memory. So memory basically stores all of the data. Memory does not have logic on its own. It just stores data and the instructions which we write as various applications or programs. And memory also has a speed limit at which it can communicate with the CPU. So as we see over here, all of the data and instructions that are present in the memory, they have to be carried inside the CPU before the CPU can actually execute those instructions. So the speed at which this data transfer happens also has a limit. So again, just a high level overview, all of the applications that we run at a high level, they are stored in the long-term memory. When we execute those applications, so for example, when I'm not browsing, my browser is stored in the long-term memory, and when I start to browse, the browser is loaded into the main memory. The computer fetches one instructions at a time and executes them depending upon what operations we are trying to do. Now we move on to the next most important characteristic of how a CPU operates. So as we see over here, or when the CPU fetches instructions from the main memory, it can only execute one instruction at a time. So if there are multiple instructions, it chooses one instruction, executes it, then it chooses the next instruction, executes it, and then keeps going on like this. So this is the major problem with CPUs. Like executing it one by one gives us an idea that if we have a lot of instructions, then the CPUs might take a lot of time to run finish those instructions. So let's take a look at, say I have a uniprocessor CPU on my device, which means there is only one processing unit on my CPU, and I have a data processing application similar to Gnuastro. So we'll keep the data processing part simple, which basically adds two arrays. And I've taken small arrays over here, but generally these arrays are very large. They have thousands to millions of elements. But let's take a small array and say, how does the CPU, when we tell the CPU to add these two arrays, how does the CPU actually see this? So as I mentioned earlier, all of the operations, all of the add operations are converted into very simple binary code, which the CPU can actually understand. The CPU cannot directly understand what we mean when it tell it to add. So all of these instructions are converted into very low level binary code, which the CPU can actually understand. So how does the binary code look like? So here's a rough representation of what the binary code will look like. So if I have like 5-6 elements in my array, the normally how a CPU will approach this problem is load the first element of the first array inside the CPU memory, then load the first element of the second array inside the CPU memory, and then actually perform the add operation. So this add operation is done by various logical gates which are present on the CPU hardware. And then when the add operation is complete, it writes the result back to the CPU memory. So this is because it can only execute one instruction at a time. So it must first complete this instruction, and then it can move to this instruction, and then it moves to this instruction, and then it moves to this instruction. And like it keeps doing it for all of the elements. So first, when the first element is added, it moves on to the second element. When the second element is added, it moves on to the third element, and so on. Now what is a problem in this? So when it is executing the first element, all these instructions, they have to wait, like the second element of the array has to wait for the first element of the array to be processed. But why does it have to wait? Because the result of the second operation is completely independent of what the result of the first operation will be. Similarly, the third element of the array also has to wait before the first and the second element of the array are calculated. But ideally, they should not be waiting, because they are really independent of each other. The third element of the resultant array depends only upon the third element of the input two arrays. It does not depend upon the first element and the second element of the array. So why do they have to wait? So the core reason they have to wait is because CPUs can only execute one instruction at a time. So now we'll try to figure out what are the solutions to it. Since CPUs can only execute one instruction at a time, and what we are seeing over here is like these instructions are independent of each other. So this instruction doesn't have to wait for the previous instructions to complete. It can be executed at the same time or before the first instruction. So we are trying to figure out a way where we can execute this instruction at the same time or before it. Just that this instruction should not wait for the previous instruction to complete. So let's see what are the potential solutions for it. The core reason why we are facing the problem is the CPUs can only execute one instruction at a time, correct? So how about we increase the processing units on the CPU? So initially we assumed a single processor CPU, which means it only had a single processing unit. So what if we increase the number of processing units on the CPU? So instead of one processor, now I have 4 processor or 6 processor or 8 processors. So that means that each processor can execute one instruction at a time. So if we go back to our previous example, the first element will be calculated by the first processor, the second element will be calculated by the second processor, third element by the third processor, and all of them will be happening simultaneously at the same time, because all of the processors will be acting independent of each other. So this is one potential solution, but the problem with this solution is that CPU cores are extremely costly. So even in modern CPUs, we usually get to see multiprocessor CPUs, which usually have 8 or 16 or maybe sometimes 32 or 64 cores. But the problem is they are extremely costly. So if we increase the number of CPU processing units on our computer, the cost of the computer will increase exponentially, because they are the most important piece of hardware on our computer. And another problem is there are also hardware limitations for this. So if you have multiple CPUs, then you also have to the operating system of our system also has to manage multiple CPUs, and they also, like, CPUs are generally also associated with heating problems. So our system will get heated a lot and fast. So the next solution for this is the graphics processing unit, which is the main reason why I'm here. So the word graphics in GPU is not really important. It has historical reasons. So the word graphics doesn't have much to do with what we are working on. We are more interested in the processing units part. So how is the processing unit of the GPU different from that of the CPU? So just like CPUs, GPUs are also instruction execution machines. So CPUs take one instruction at a time, execute it. GPUs do the same thing, but their processing units are very different from those of the CPUs. How are they different? So the CPUs are extremely fast and they are very generalized, so they can execute any instruction that is given to them. However, GPUs are designed for a completely different purpose. So the CPU, as I mentioned earlier, was the brain of the computer, so it must have the ability to execute any instruction that is given to it. However, GPUs are not the brain of the computer. They are just designed to solve one specific problem that the CPU was facing. So they are designed in such a way that they have different hardware components on them. So this means that a single instruction which can be executed on the CPU will not necessarily execute on the GPU as well. So this is the main architectural difference between the CPU and the GPU. So this on the left hand side we have a multi-core processor, which is the CPU. Generally we get to see 4 to 8 processors. So this is an example of 4-core processor. So it has 4 processing units, the green parts of the image. It has 4 processing units and each of them can operate independently. But we realize that we cannot increase it beyond 4 or 8 or maybe 16 or 32. We cannot make it 1,000 or a million. But in our case, when we are dealing with astronomical data sets, the number of elements in a single array or a 2D array or image is basically around 10,000 to millions of input in a single image. And when we are performing an operation to add 2 images or multiply 2 images or convolve a single image, at that time all of the elements need to be computed independently. So the one pixel does not have to depend upon the value of the other pixel to be calculated. So that if we have a million of element in a single image, we cannot have a millions of cores on our CPU. So this is the problem that GPU solve. So on a GPU we have different types of cores compared to the CPU, but we have too many of them. We have thousands to millions of cores on the GPU. And similar to the CPU memory, we also have a GPU memory where it temporarily keeps the data which is currently being executed. So CPUs are designed with variety of logic gates, which means that since they were the brain of the computer, they must have the ability to do any operation that is given to them. So they have multiple hardware units on them, which are responsible for executing each instruction of a particular type. On the other hand, GPUs have very few hardware units because they are not expected to execute any instruction that is given to them. They are specifically designed to execute instructions which follow the SIMD philosophy. So SIMD stands for single instruction multiple data. which means that the GPUs are only good when we have an instruction which follows the SIMD philosophy. So what is the SIMD philosophy? So SIMD says that when we have a single instruction, say the instruction could be like convolve an image, and we have multiple data points on which we have to execute that instruction. So say we have an image which has 1,000,000 pixels, and we have to convolve that image. This is a very common operation in astronomy. So say we have an image which consists of millions of pixels, and we have to convert the entire image. So what we notice over here is on all of the single pixels of our image, the operation that is to be performed is the same, which is the convolution operation. But we have multiple data, we have millions of pixels, so we have to execute that instruction on millions of pixels. So this is where the SIMD philosophy is derived from. When we have the same instruction and we have different data points on which we have to execute that instruction. So what SIMD does is it loads a single instruction, but it loads multiple data. When we load our image which we have to convolve in the memory, normally the CPU will take one instruction and one data. However, a GPU will take one instruction and multiple data. So if a GPU has say 1,000 cores, then it will take 1,000 data points at the same time. So data points will essentially be pixels in our image. So it will take 1,000 pixels and convolve each pixel at the same time, because GPUs have 1,000 cores. So a very good analogy to understand what the SIMD philosophy is, when we have say a single PhD student at our university, so they can basically, they are very skilled and very fast at doing whatever they have excelled their whatever they are majoring in. So they know their skill very well. They can do any task that is given to them. So, and they will do it very fast, and they normally outperform any other, basically a graduate student or a high school student. But when we have like a lot of data points, and the operation that we have to do is not really complex, so the GPU is similar to the case of 1,000 high school students. So a single high school student is no comparison to a single PhD student. But when we have 1,000 high school student and we have to execute the same instruction, so let's take an example of picking up a ball. So if you are picking up a small marble from the ground, then calling a PhD student for that is not really a good task. Or say we have a mathematical operation that you have to perform. If it's a simple addition or subtraction operation, then calling the PhD student for it is not a good task, because any single high school student can also do it. But say now we have to do addition operation 1,000 times. So still, like this, a PhD student can do the can like add numbers 1,000 times, but it will not be as fast as 1,000 high school students, because each of the high school students can add this single number. One high school student will add one number, and all of the 1,000 will do it simultaneously. So since the operation was not complex, even a high school student can do it, and they will outperform the PhD student in this case. So this is a summary of what are the major differences and what are the design principles that we consider when we design a CPU and the GPU. So the CPU is designed for general purpose. It is supposed to be the brain of the computer. And then it is emphasized specifically to execute a single thread, like a single stream of instructions, and do it very fast, because it has to execute multiple applications at the same time. So it must execute the instructions very fast. However, on the other hand, GPUs are designed for special type of operations, where each of the operation can be executed independent of each other. And yeah, so that's why they have a parallel architecture to them, where each core operates independently of the other core. Similarly, the memory is optimized for fast retrieval. Since the CPU has to execute instruction very fast, the memory, like the data, should come from the memory very fast, so that it can actually execute those instructions. On the other hand, GPUs are optimized to collect a huge amounts of data, because GPUs take one single instruction but take thousands to millions of data points at the same time. So the amount of memory that should come, that's the main emphasis. The amount of memory should be huge in GPUs. And now, once we have understood how our GPUs designed differently and for different purposes than the CPUs, now let's understand how does, on a single computer, how do both CPUs and GPUs can coexist? Because both of them are essentially responsible for executing instructions. Like no other component of the computer, like our input output, our memory, none of them are responsible for executing instructions. Only the CPUs and GPUs are. So say now a user wants to run an application. Now which should those instructions be executed on the CPU, or should those instructions be executed on the GPU? So how do we decide these things? So in general, any application has a mix of parallel and sequential parts. So sequential part is where each operation is dependent on the other operation. So a good example is calculating the nth Fibonacci number. So if you want to calculate the nth Fibonacci number, then we must know the n-1 and the n-2 Fibonacci number, because without calculating those two numbers, we cannot calculate the nth Fibonacci number. So the nth Fibonacci number must wait for the n-1th and the n-2nd Fibonacci number to be calculated. However, parallel tasks are when the nth element does not have to wait for the n-1 and the n-2 or any other element. So if we are adding two arrays, very big arrays, then the result of the nth position will be just the sum of the nth position in the input arrays. It does not depend upon the n-1 or the n-2 arrays. So these are parallel tasks, and in general any application has a mix of these two parts. So what we do is we let CPU remain the brain of the computer. It is responsible for doing all of the things that it used to do previously. However, whenever we encounter parallel tasks where each operation is independent of the other operation, we offload those tasks to the GPU, because we know that GPUs will perform extremely well as compared to the CPUs when the tasks are parallel. Okay, now this is like how it is generally represented at a low level on a general computer system. The host is the CPU, which is the main brain of the computer, and the devices are the extra processing units similar to GPUs, which are designed specifically to execute specific type of operation. So when we encounter those type of operation, the host sends out those instructions to the GPU memory, to the GPU or any other hardware accelerator. So now we look back at our original picture where I explained the initial how a computer system is represented. Now we have like earlier we only had a CPU and the main memory, but now we also have a GPU and a GPU memory. So now the normal flow of the program is, so say I want to multiply two matrices on my computer. So initially those matrices are stored on the long-term memory. First, they are loaded into the main memory, and the command is still under a CPU. So it is deciding what to do with those, and then it realizes that a matrix multiplication is a very highly parallelizable task. So what it does is, the first it loaded the data into the main memory. It copies that data to the GPU memory. Remember, GPU also had their own memories. This was designed specifically to load a huge amounts of data at the same time. So what it does is it sends out the data to the GPU memory, and it tells the GPU that I have given you some data, and now you have to multiply those two matrices and store the result in your own memory. So GPU takes each element, like it takes all of the data at once, and then it executes the multiply operation on all of them at the same time, because GPU has multiple processing units. And then when the results are stored back to the memory, the results are copied back to the CPU memory, and then the CPU can display the results to the user. So this is how a heterogeneous system works, when basically we have multiple processing units on a single device. Now we come on how do we program these systems. So as I discussed earlier, the hardware of CPU and GPU are different because they are designed to do different tasks. And a single instruction that CPU will understand will not necessarily be understood by the GPU. So when we are telling a GPU to do something, we must explain it in the language that it understands. So we must program it separately. So there are various high-level frameworks available to program these GPUs. Here's a comparison on some of the major ones. So CUDA stands for Compute Unified Device Architecture. This is developed by NVIDIA for its proprietary software. It's a proprietary software by NVIDIA, and this is designed specifically for NVIDIA GPUs. So it's not open source and it's not heterogeneous. So heterogeneous in this context means if we have a GPU as a device accelerator, so as I explained, GPUs are responsible for executing highly parallel tasks. So similarly, there are different types of tasks with different types of hardware come in. So FPGAs are another hardware accelerator. So if we write some code on CUDA, that code will only execute on an NVIDIA GPU. It will not execute an AMD GPU or Intel GPU or any other FPGA as well. So, and then the next framework is OpenCL. So it is an open source standard maintained by the Khronos group. It is open source as well as heterogeneous. So if we write our code in OpenCL, then it can be executed in any GPU, and it can also be executed on FPGAs or other hardware units. Then is one API developed by Intel. It is also open source and heterogeneous, and HIP is developed by AMD. So it is not heterogeneous. The only heterogeneous in HIP is if we write our code in HIP, it can be executed by AMD GPU as well as NVIDIA GPU, but it cannot be executed by any other GPU. So they specifically focus on only two types of GPUs, but not a general case. And now, like as I mentioned, so we have to program the CPUs and the GPUs separately.
So I'm too muted.
Sorry to interrupt. You have 5 more minutes.
Okay, sure. So like in this case, we can see that the above code is for the CPU, where it iterates through every single element, and then it does the core operation. So this operation and this operation is the same, but when we write the code for GPU, we only write this once. But when we are writing this for the CPU, this is we have to write this for all the elements. So there are extra for loops out there. And now these are the results that I got. So I choose the spatial convolution operation, and I choose an input image of 10,000 by 10,000 size of 10,000 by 10,000 pixels, which is similar to the JP-CAM that is used at the institute. And the kernel was 7 by 7. My Intel core, which was responsible for executing the Gnuastro code, like the existing Gnuastro code using the Gnuastro library, it was run on an i5 9th gen computer, and the GPU I used was the NVIDIA GTX 1650. So if I execute the convolution operation using the existing Gnuastro library on this input, I get a time of 26 seconds. However, when I do this on the GPU, so the total time taken is 1.4 seconds. However, when we are doing it on the GPU, there are also different aspects to consider, because as I mentioned, first you have to copy the data to the GPU memory, do the operations, then copy back to the CPU memory. So there is an extra overhead everywhere. So the total time is actually a sum of all of these times, but we only care about the convolution operation because this is what we are trying to optimize. And if we look at just the convolution operation, we notice that it has over 400 times faster than the CPUs. So what we realize is this the main operation is optimized by over 400x. There are some data transfer over it that we are currently trying to solve, but we can see a huge speed up when we try to execute a parallel task on the GPU. So yeah, most of the time of this 1.4 seconds is taken by initializing the GPU and copying the data to the GPU memory and copying back to the GPU memory. But the core operation, which is the convolution operation, it is optimized a lot. And then this was also an experiment that we did. We tried to run the same code on the GPU and the CPU. So as I mentioned earlier, we have to write different codes, but most of the frameworks are derived from the C or C++ language, and Gnuastro is also written in the same language. So apart from the extra code that GPUs have, which involves initialization and data transfer, we wrote the same like the actual convolution operation remains the same. So we tried that as well, and just to confirm that we are getting the same outputs from both, we viewed both the images on DS9. So the left one is from the GPU and the right one is from the CPU. And so a summary of everything is, CPUs are the brain of the computer. They are responsible for doing everything that we do on the computer. However, CPUs have a limitation that they can only execute one instruction at a time. So when we have huge amounts of data and we have to execute the same operation on all of them, and in these cases, they will execute it one by one on each data point. So they become very inefficient. So this is where GPUs come in. GPUs take one instruction, but they take huge amounts of data, and then they execute that same instruction on all of the data at the same point, at the same time. So so thus GPUs become very fast at parallelizable tasks. So that ends my presentation. If anyone has any questions, please let me know.
Thank you very much. Questions? I have a question.
Yeah, sure.
GPU parallelization is already implemented by default in Gnuastro, or you have to activate something, or
Oh, okay. So when you install a GPU on your computer, so each of the GPU vendors provide their own drivers. So drivers are basically an interface. So when you want to do something on the GPU, you talk with the driver, and then you tell the driver what to do, and the driver does all of the operation, and then it sends back the result. So the driver is provided by the provider. So when you install a GPU on your device, you can download the driver from the website of the manufacturer, and then like all of the providers also provide programming guide, like how you can program the GPUs. So you can, depending upon what GPU you have, you can follow the respective guide for it.
okay, and it will work in either in NVIDIA or
Oh, so as I mentioned, my current GPU is the NVIDIA GPU. It is a 1650 GPU which has 4 gigabytes of virtual memory. But like the code I've written it in OpenCL. So this means that without making any modifications to the code, I can run it on any other GPU or any other FPGA as well. So that's the power of OpenCL. It is portable and it is heterogeneous. So it does not matter what GPU I have. Like my laptop had an integrated NVIDIA GPU, so I was using that. But if we take this code to any other system, it will, and it has, regardless of what GPU it has, it will give the same results.
Okay, so just to finalize your answer, Labib has been working a lot on the infrastructure, so it's still in the development branch. It's not in the main release branch because he built the infrastructure. Now we have to actually put like he showed the convolution, but there's many other parallelized operations that. But once since this infrastructure is now ready, we can easily bring in all of those and then merge it into the master branch. Yeah.
Perfect. Thank you very
It's
much.
a lot of work to learn OpenCL. Because it's a different paradigm. You actually give the code as a string, and then the GPU compiler compiles it at runtime. It's really interesting. It's a whole different way to work, let's say, in programming.
Okay, any more questions? Okay, if not, we thank again Labib.
Thank you for the opportunity. Yeah. So should I stop sharing my screen?
Yeah.
So, thank you.
It's 60 slides, that's how we like it.
Not become the part, I just say. Okay, so next one.
Okay, so hi, I'm Adri, and I've been here this summer working at CEFCA, as many of you know, together with Carriños on white dwarfs, and now I'll present the work that we've been doing. So first, a little bit of introduction. What are white dwarfs? So white dwarfs are stellar core remnants of stars that have a mass less than 8 to 10 solar masses, and they're composed mostly of hot electron-dependent matter with a cooler thin atmosphere. And their masses range from 0.17 to 133 solar masses. Here I show the typical HR diagram from the collaboration. And the white dwarf sequence would be this one. And so white dwarfs enter this sequence roughly at this area with a temperature of 1,000 kelvins. And they evolve, cooling down following this sequence, reaching here temperatures reaching a temperature of about 1,000 kelvins. There's mainly two types of white dwarfs. One that are called DAs, and they have hydrogen-dominated atmospheres. And then the other type would be non-DAs that actually have helium-dominated atmospheres. And in color diagrams, here I show one that shows the G minus R color against the U minus R color. We can see that they separate into two sequences. That one would be this sequence corresponding to DA white dwarfs, and the other one would be non-DA white dwarfs. And so the work that we've been doing this summer can actually be divided into two projects. The first one would be white dwarfs in the ultraviolet, for which we have used JPAS DR2 data. That's, as all of you know, a photometric survey with optical filters that covers for DR2 an area of 2,176 square degrees. And for the second part of the project, for which we studied white dwarf variability, we have used JVAR DR1 plus, because we actually use more fields that actually will come up. And that basically JVAR is a survey that observes in 11 epochs and 3 observations per epoch in 7 optical filters. And there's extra observations that are called high frequency observations that are actually done in 5 different filters and covers an area of approximately 200 degrees, which is like about 10% of the Earth's. So for the first part of the project, white dwarfs in the ultraviolet. The idea is that we started from this work that Carolina's did, in which they studied the spectral evolution of white dwarfs. The idea was to fit these models for DAs and non-DA stars and basically obtain these parameters. So the temperature, the gravity, the parallax that came from Gaia, and the probability of each source to be a DA. Here it reads PDA, but I will be using pH as the same. So basically, we extracted the probability of a star being a DA or non-DA. And here I put 2 examples of the spectral energy distribution of 2 of these objects. So once we had this, the idea was to complement the study with ultraviolet data. We wanted to match J+ and the GALEX catalogs for the white dwarf sample of this study. Very simply, GALEX is an ultraviolet all-sky survey in 2 bands that has a far UV at this wavelength and a near UV at this wavelength. And then once we had this match done, the idea was to study the properties in the ultraviolet and see what we could gain from these 2 extra optical ultraviolet filters. And so from the initial sample of the J+ white dwarfs, that was 5,111 sources that I present here in the optical color diagram. And this is the temperature distribution. Once the match was done, using a 4 arcsecond match radius, we obtained that for the near UV filter, we obtained for 4,853 stars. And this is their temperature distribution that we can see shifted a little bit to the hotter range because cooler stars emit less in ultraviolet, and so they're harder to observe. And when we included the far UV filter, this is the stars that we found. And we see that the distribution now clearly shifts to the hotter region. So all in all, what we decided to do was to do our study covering the sample at a temperature higher than 10,000 kelvins. This is the remaining objects. Here I present the color diagram, in which I put the G- I color, which is sensible to temperature, and the U- R color, which is sensible to the separation between DA and non-DA stars. And we see that here I colored them by the probability of being DAs, with this being the DA section and this being the non-DA sequence. And now this is the extra color diagram that we obtained. That I show the U- R color and the far UV and near UV color. And what we see is that these 2 sequences, so the separation, so the contrast among separate sequences is enhanced. And so we gain that in cooler stars, so it would be this region and this region, this separation is enhanced. And here I put 2 examples, so the ones that I previously showed, that these would be the optical J+ filters, and we added the 2 GALEX UV filters, and these would be the models. So the idea was that these models were used to calibrate the optical filters of J+, and so it makes sense that they work. But these 2 extra points were extrapolated from these models, and so the idea was to see whether this was working or not. And we recovered results that actually were pretty good. But this is 2 examples, and want to see how it works with the overall sample. So here I present our samples are composed with different models. The bluer colors correspond to DA models with gravities ranging from 10 to the 9, 8, and 7. And the redder colors are non-DA models with, once again, gravities going from 7, 8, and 9, 10 to the 7, 8, and 9. And then what we see is that in the optical, since they were used to calibrate the sample, they work perfectly. And so the idea was to see how they work in the ultraviolet. What we see is that for DAs, so the yellow points, we recover a little bit what the models tell us, that where they converge, we see no dispersion in our sample. But when they diverge, so the different gravities cause a divergence in the sample, we recover this dispersion in our points. When it comes to non-DAs, however, this is not really exactly what we recover. So we're in the places where the three models converge, we actually observe a very high range of dispersion in our sample. And so that means maybe that dispersion comes from the errors, or maybe there's some physical processes that these models are not contemplating. And so they are not good for, well, not as good as they could be to explain non-DA white dwarfs. And so we also, apart from the outliers, we also recovered some misclassified, well, we have some misclassified points that are located clearly in the DA sequence, but are classified as non-DAs. So what are these things that could be causing these misclassifications and outliers? So we think that they could be, for example, unresolved binary objects, cataclysmic variables, the presence of metals in the atmosphere from accretion, or maybe the presence of carbon from the cores of white dwarfs, or some other physical processes. And so on that topic, just to say that this is a very ongoing research right now. So there are lots of papers that are coming out on this topic, and it's a state-of-the-art thing that's being studied. One of the things that we decided to study was binary candidates, which are those objects that the model predicted a mass lower than 0.45 solar masses. Why would this why would these objects be binary candidates? Because the stars that would create these white dwarfs haven't had yet time to die off and create them. So it wouldn't make sense. Therefore, they have to have been created either in binary systems by mass accretion, or they will be two white dwarfs that are not resolved. And so we consider them as a brighter object and so less massive. Here I show their location in the ultraviolet color diagram. And when we color them with our probability of being DAs, we see a lot of misclassified objects. So basically, these binary candidates accounted for the outliers in this blue region of the DA sequence, and also for 60% of the misclassified objects that I was talking about. Why does that happen? Basically, here I show a simple, well, a typical case in which you see the contribution of the white dwarf complemented by the contribution of a redder companion. And so when the model has to fit this, its supervisor is completely unable to predict this. So that's why we have these misclassifications and outliers. Another example that we found that was super interesting was this object that is a white dwarf that has that has contaminated photometry. So basically the model works perfectly in the optical range, so in the J plus range, because these two objects are resolved. But when we go to galaxies, these two objects are not resolved. And so the model was not able to predict this because they would be the contribution of them too. But if you recall, this was a redder object, so it wouldn't really make sense to have such a high ultraviolet contribution. So when we looked at the redder object in J and J plus photometry, we saw that this red object has itself a white dwarf companion. So when looking into Gaia, looking at the parallaxes and the proper motions, we basically think that this is consistent with it being a triple system. So this system in the Gaia filters has this white dwarf plus the contribution of an unresolved white dwarf that is hidden here. And so obviously it's completely unable to predict this in the model. Another thing that caught our attention was these 2 points, these 2 outliers that seem to be in a very isolated position by themselves. And so we went to look them up. And the models, once again, seem to work fine in J plus photometry, but not in galaxies. And when we went into the literature and found the spectra, we found that they have carbon-1 absorption lines. And I say they because the other one has the same. The first one was a DA object, and this one is a non-DA white dwarf. And so the effect is the same. The model does not predict. And these objects also have carbon-1 absorption lines. And so the thing that happens is that this presence of carbon changes the absorption of the atmosphere, especially in the ultraviolet. And so we receive less flux than we would expect. All in all, having done all of this, what we can say is that we have successfully matched the J plus and Galaxy catalogs for the white dwarf sample study. And then for the study of their properties in the ultraviolet, we see that in the ultraviolets, the two sequences, so DA and non-DA sequences, are clearly separated. And we can also say that there are hints of missing physics in the non-DA models that we have used, as we've seen. They do not consider binary candidates, carbon in the atmospheres, and others. And also that the ultraviolet is very sensible to unresolved binary white dwarfs. So that's for the first part of the project. Then the second part of the project was on white dwarf variability. So very briefly, DA stars, so DA white dwarfs, are expected to pulse when they go through this region, which is the white dwarf instability strip. And these stars are called ZZZ stars. The idea was to use J-bar data to see if we could study this region. This would be a typical curve of a ZZZ star. And these are their pulsating properties. So their periods go from 100 seconds to about 1,500 seconds. And their amplitudes go from very few percent up to maybe 30%. But the typical stars will say about 1 to 10%. So very little variations in their magnitudes. So it's variations that it's kind of hard to observe. So our goals was to first find how many of the white dwarfs that we had were observed in J-bar, then study their variability and study whether this data showed this instability strip. So this was the sample that we found. So from the initial J plus white dwarfs, we recovered 592 J-bar white dwarf, which is about 10%, which makes sense because J-bar observes about 10% of the R2. And for each of the stars, we had a light curve like this one, in which, well, for each of the 7 filters, the different observations. Then this is their distribution in the temperature against mass diagram. And in here, we have the instability strip. So how do we study the variability for each star? We decided to fit a Gaussian into this parameter that was the magnitude for each point in relation to the mean of the magnitude for each filter divided by the error. And so from this, we could recover the variance of this Gaussian. The idea is that as a non-pulsating star would have a variance that's consistent with 1, and pulsating stars would have a higher variance. And so this is the resulting variance distribution. We really couldn't see this in first time, so we decided to put it this way to see what we were recovering, and then we calculated the mean of these variances inside the instability strip, so for the blue points, or outside of the instability strip, so for the red points. And as you can see, we really couldn't see any difference, and in fact, it came out lower than outside the instability strip. So we didn't really understand why we weren't recovering any, like we weren't seeing any variability. And so what we decided to explore was what parameters would affect that. And one that really was important for us was the number of observations, mainly because we had some trouble fitting the Gaussian to those objects that have very little observations. So the fittings were not always good. So we decided to study the relation of this difference as a function of observations. And for that, we went to the facility, which is basically a 2 night cadence public survey of the entire northern sky in the GNR bands that's based in Palomar Observatory in California, here. And when we did that, the idea was to obtain the ratio of these two mean, so the mean of the variance inside and outside of the instability strip, so the ratio as a function of the minimum number of observations that we require each source to have. And so this is the distribution that we observed, that we recovered of the parameter. And here we showed the number of ZZZ stars that we had that had this minimum number of observations required to see if it still makes sense to do a statistical analysis of the population with these numbers. And what we observed is that at about 50 observations, these parameters stabilized and show a 10% increase inside the instability strip than outside. And so at the beginning, I said that J-bar consists of 11 epochs of observations times 3 times, so 3 observations per epoch, that's 33. They will not be in this region, so maybe that's why we weren't observing that. Another thing that we decided to do was to see what information was inside of the light curves. So basically, we found that one of these objects had been observed and it had a light curve, period, amplitude, and a phase. Well, not a phase, but actually 3 phases, because we could not know which of the observations was matching this light curve. But what we could do was study the 3 phases and compare them to our data. So we fixed the period and the amplitude of the light curve, and we fitted the 3 phases to a best fit of our sample. Therefore, we could recover the light curve of this object that matched JVAR data. And then doing this by each field, for every filter that we had for these high frequency observations, we could recover the amplitude of this pulsation. Well, this source was supposed to have a 2.18% of amplitude, and we recovered 0.5 in the G band and not so lucky in the rest of bands. But well, that's what we recovered. So all in all, from the study, we have done, we can say for white dwarfs, with more than 50 observations, we can make a statistical study of the population's variability. That when there are high frequency observations, if we have the periods and the phases available, we can reproduce the light curves sort of successfully. And unluckily, what we had to conclude was that JVAR data is not suitable to study these ZZ stars. So maybe there's another approach that can be taken. So for example, we tried other estimators of the variability, like the MAT estimator, and we recovered the same results. So we saw no difference inside or outside the instability stream, but maybe there's other approaches on the topic that could work. Anyhow, the ones that we have tried haven't, so feel free if anyone wants to try. And thank you. Muchas gracias. Thank you.
Thank you very much. Perfect timing. Questions?
2 questions. First of all, thanks very much. Very nice work. Is that really the only ZZ setting we have in JVAR? Out of the 592, we only have one known ZZ setting?
One observed that has a period, amplitude, and phase. So you had another one that did not have, so another that was identified, but they didn't further observe it to determine its period. So
We need more. We need more observations of JVAR. Obviously, like the first thing that you would do is try to find known systems and see if the light curve actually catches the variation. But with only one, well, yeah, that's not. But having said that, probably not very surprising that JVAR is not suited for ZZ settings. It's not thought to be.
Yeah.
So basically, yeah, you're confirming what we kind of knew, but anyway, it's really good to see. And the second question, if you go back to your color diagrams with the models, to the very beginning, you use a mixed hydrogen helium.
yes,
So A, why not pure helium? And B, do you try different mix recipes,
okay.
or is it a fixed one?
I was given this model. No, but what I know is that purely hydrogen atmospheric models don't work as well as mixed helium models, don't work as well as mixed hydrogen helium. So this one has a ratio that's 10 to the minus 5 mix. There's others, but these are the one that was used in the previous study. So the idea was to kind of like expand this study with 2 extra filters, and that's what we limited ourselves to.
I had a comment on this. The right hand plot. The right hand plot is basically inspired from the other plot by USH and collaborators, right? And the comment I really want to make is this basically shows you that if you use the 12 filters of J plus instead of using any other 4 filters or 3 filters, your ability of differentiating between between different types of objects is significantly better, just because 12 is larger than 4, basically. I comment more about JVAR, but I will not. All the bizarre objects that you found, binaries, blah, yeah, pass them over. And and because those are obviously needed to be checked in, say, JVAR, of course, ZTF, Assassin, but with the triple system you told me yesterday, yeah, I spent yesterday I wanted to do something else. Basically, I spent the whole day, and turns out there's no spectra of that object ever, nowhere to be found. I still have to check the GTC archive. If it's not in the GTC archive, Lumbreras is going to write a But it's an awesome work.
Okay, more questions?
Quick thing. Great work. Back on the very beginning, you did a cross match with Galax. Did you do it with an available catalog, or did you query the database?
We queried the database.
Yes.
Yeah.
And wouldn't that be great to have like a cross match with all the actual Galax data that is available, a cross match with JPLOS? Because there were, I don't know if you checked, but there were, I guess, many more objects this way than with
Yes, there were more objects this way. I don't remember the exact numbers, but maybe like 500 more or something like that.
it was 5,000 something or 6,000. Just wanted to, I guess this was the way, I mean, this is a trick question because I have already also done that with Carlinhos, with his code. But I just wanted to say it out loud so everyone knows.
Yeah, the problem is we tend to use AIS, the old imaging survey of Galax, instead of accessing directly the Galax catalog in, Galax detections in MAST. And that is where, what you're saying, that's where all the detections are. Plus, you can get Galax light curves there.
It is.
More questions? No? Thanks again, Adriana. So next one, Pedro Hernández, who's going to give a talk about the effect of headset compression on astronomical images.
Hello, as you introduced me, I'm Pedro. Most of you will know me as this one. I've been working with Mohammed and Alex during this summer to study the effects on the compression. And the first question that might arise to you all is, why do compress images at all? I mean, we want all the information, why risk and lose something, if that's the case. To answer that, we're going to check the JPLOS data registry footprint, which is here. And as you can see, the size of storage needed is quite large, and that is compressed. So if we were to use the uncompressed images, we'll be talking about 4 times at least a bigger needing of storage, and that translates into more cost. And it's very expensive to storage that many data, which would translate also in not being able to have the summer internship or even do some PhDs or even postdocs works because of that. So it is really an important fact and important matter to study. But now, we do need that we have to compress the images. So the next question would be, we know that there are some lossless algorithms to compress images, so why don't we use them? We have ANSI, why don't we use that instead of DLG compression? So we are going to use this beautiful image of the class of the Messier 106. And we're going to take a little section of 10 by 10 pixels and study with their pixel values. So, as you can see clearly, these are saved in float 32, which means that each pixels need 32 bits to store the value. And if you check, you wouldn't find a single value repeated in this section. So the GANSIP wouldn't work properly on compression. Even more, if we take the whole image of the child, we'll be talking about 90 million pixels total, each of them 32 bits, no one repeated, and GANSIP would be like useless in this case because there's nothing to compress except for the headers. So if you use GANSIP, okay, you would save some kilobytes, but that's really doing nothing. So yeah, we cannot use at all GANSIP. So now, how does work our FC compression? Okay, we're going to start with the same tile that we had before. It's the original one with float 32 pixel values. Now, the main difference between this lossless GANSIP algorithm and a lossy one, such as FC compression, is basically that the process of integerization of the pixel values. We start with the subtraction of the minimum value. So we can set the minimum of the image at 0. Then we divide by the maximum, and we have the maximum set at 1. So we have the range of pixel values from 0 to 1. And we finally just multiply by 255 and round it to eliminate the decimals. So we have set the maximum at 255 and the minimum at 0. You could ask, why is that important? So we have managed in very few steps to reduce the bits needed from 32 to 8. So now we have reduced very much the storage. But not only that, we have also created some repeated value pixels. As you may find, here we have some repeated, we have some over there, and if you check, you will find even more, which in a 90 million pixels image. I mean, there's a lot repeated. The thing is that we can compress and move the image. It uses like it compressed by 32 bits by default, and it takes the information in a bin table position. But the main step is this one. This is the much reduction of the image. And the good thing is that you can go back. When you have the image, you can go back to the original one, but with losses. During this interization process, you have rounded the decimals. So even though you know the maximum and the minimum, you are not going to restore the true original values. As you can see, this is just a first result drawn by Mohammed. If you take a mock image of the galaxy, you noise it, and you take the difference between the original and the compressed image, you will find that there's some noise added in the pixel values. And that's what we want to study, really, because we want to know exactly what consequences that this added noise and how it is affecting our science, or if it's not affecting. And so we start our simulations, because the ideal cases are more easily studied. So we have divided this in two separate, as well as Adriana. We have in two blocks, which is the integrated measurements. We take images with lots of objects, and we have done the aperture photogrammetry for more grid of stars, which will be this image, more grid of diffuse objects, the image one, and we have also performed the test on multi-stack images, which is a very important one. I'll explain why later. And we have used real images from HST because they weren't already compressed. So this is not the class would be an exception. So the first one, we have made 50 simulations of 64 stars. So we have 50 images just like this, but where we change the magnitude and the noise silent, and we have studied the flux in each of them, in the compressed and the uncompressed one. And the difference show that for most of the higher S2 SN objects, the difference is not really relevant. There's no significant difference that will be worrying. But when we go to this part of the lower SN ratio, it's kind of get more tricky. In the case of the Gaussian noise, it is much more relevant because the Poisson being already integers, the effect of compression is less important than in the case of the Gaussian, but it's still there. But in that case, the error is not very, the difference is not very significant for the stars because they are the sharpest objects in the sky. So it is true that there is some effects, but it is mostly on the lower SN objects, around 3.5, from 0 to 3.5, it would be the most affected area. But now we're talking about diffuse objects. These are trickier, as you know. Even though the center is quite bright, when we get in the diffuser areas, we have lesser single to noise ratio, which translates in a bigger differences. As you can see, even though most of the objects are around 0, the scatter is quite big. We're talking about that we have added another error to the measurement, and the error bars shows, I don't know this photo, we have checked them and show that for the same range more or less, we have some problems in there. So it's something that we have to check really, because we might be losing some information in that kind of objects, and they're being used by some astronomers, which is worrying. So we have done this for 4 different SSD indexes. This is from 0.5. We have done it for 1.0. Once again, the scatter is pretty big. And once again, it is less remarkable for the Poisson, but still relevant for this kind of objects. For 4 and 10, they are the most scattered ones. And this is worrying, to be honest. The low range of essential noise objects is something that we have to study with more detail, because we're having some not really good results in the area. The rest is all right. Finally, this is the important test that I was talking about. So when we are stacking images, there are 2 strategies. You can pack them once they're compressed, or pack them when they're uncompressed and then pack them. Usually, what we are generally using is the default one. So we are stacking some already compressed images, which if there is an effect on one of them, you are completing the effect to the others. So in this case, we have compared the compressed stacked images with the uncompressed, so no compression at all. And the effect is, once again, we can clearly see it. And to study if there was a difference in the strategy to use, we have tried to use the uncompressed images and compress them once they're stacked, and compare them to the previous ones. And the results are that the compressed post-stacking, the effect on the compression is lower than in the post-compression. Okay, and finally, we've tried that these on real images, just to show, because this is not as easy a scenario. And we have done it in, as I said, in ASC images in 4 different features, and the results are similar, but you can see they're not that worrying. The scatter is less general than in the previous one. This may be an effect of the apertures we used, because we used the same size of the apertures compared to the diffuse object. We don't use an aperture including the whole length of the object. and including more noise as well. So this should be an effect of that. We will be studying this part in the future to see how different approaches affect the effect of the compression. And then finally, we go to the result measurements. This work has been carried by Alex Lee in the Hong Kong University, and we've divided this basically into different parts. The mock simulations, we have studied the radial profiles, and then we've carried morphological measurements in the real images, and here are the results. So here would be the mock galaxy with the noise, and the aperture used to study the radial profile. As you can see, the radial profile in both of them is pretty similar. The difference is near zero, and the ratio is nothing really to worry with. It's what we would expect from something that is not affected. So it seems that result images are less affected by the compression, which is what we would want, since they have more great simulation ratio. And we have done for various range of simulations, and the results were similar to all of them. Finally, we've taken the M81 galaxy. We've detected it and added some different kind of noises to see how different noise affect the compression, and measure the different morphological parameters. As you can see, in most of them, there is nothing really worrying or happening because of the compression. There's some offsets in the centers and also in the position angle, but generally this will be explained by the bigger noise, and they are between the error bars, so it could be just an effect of the error. So all in all, it is consistent with what we've done. So in conclusion, we've performed several tests on different types of images. In the case of the integrated measurements, we've concluded that high signal to noise ratio objects don't seem to be affected or are less affected by the FC compression than the lesser ones. Not the best scenario for the low SN objects, which seems to have be affected, and it's quite visible on the reflex or average percentage measurements. And gladly, for the resolve measurements, we don't really see that much of an effect. And we, at the moment of this project, we are happy because this is ongoing. We are still preparing some other tests, and with the ones we have, we are adding some other variations such as the apertures, and we want to see how the detection and segmentation might affect, because that is also an important feature. For example, I can forward some information. When I was working with the HD images, I couldn't compare the flags measured with segmentation because there was just different numbers of sources, but we cannot say really if there is a difference because it might be some spurious detection, so we have to still study deeper in that direction. Well, this is pretty much it. Thank you for listening and for the experience in the session. It's been really great. Yeah.
Question?
So, would this be worrying for the study of low surface brightness features in galaxies, like a tile that's like Arrakis is gonna do?
I mean, if there if the signal noise ratio, it apparently could be an issue. We can study even more to see if with images such as catalogs and such as the HST, we have those problems, but the deeper you go in the sky, the less resolution, less signal noise ratio you have, there seems to be an issue. It may be something that we can save because the algorithm after interpretation has some values that can be personalized for each. So we can study also how varying those parameters affects the image or if it's just the interpolation, which would be the worst case scenario, really, because you cannot really do much about it. Questions?
A good old obsession of mine. 4 stars. What would be the lowest signal to noise with which you would work?
I mean, I don't have the number, but I'll check it and send it to you.
Thanks.
So we can see the plot, right? If you
Oh,
go to
yeah.
the stars.
The thing about stars is that they're less problematic than the galaxy ones. So a bigger number should be alright, but the exact number I would have to tell you, but it is bigger than the if you could go farther than 3.5.
I normally cut at signal to noise 10. If you tell me that I can go down to signal to noise 3,
10 you usually are on the right.
but if you say that I can go down to signal to noise 3, I'm happy.
I'll check that just to be sure, but yeah.
Stay at 5,
Like in the case, now for the case of stars, we see the distribution is almost flat, right? I mean, if you take a beam of the signal to noise, like say signal to noise 5, and then we will draw the distribution. Now later Pedro is going to do that. That would be, it doesn't look too Gaussian, it looks almost flat. So this is something we have to investigate. Why it's it may be the effect of the uniform distribution of the integerization. Because when you integerize something, you get a uniform distribution. You don't get a Gaussian noise. Maybe it's because of that. But when you go to galaxies, we see that there is a sharpness in the center. So you see the distribution becomes. There's more objects with 0, but then it becomes more like a Gaussian, let's say, less flat. The center is peaky, but the scatter is really, we have to, this is really worrying. Like signal to noise 4 or 5 is what most people in galaxies use. And at 5, it's relatively, it seems fine. But at lower signal to noises like 2 or 3, it becomes almost half of the noise is because of the FC compression at very low signal to noise.
And why this is not affecting the radial profiles? You go to lower signal to noise.
I think we don't see it too much over there in the radial profile because we're summing over huge numbers of pixels, but in individual objects, these integrated objects are relatively small. Maybe it's because of that. And it's a perfect radial profile, so it's a perfect ellipse, and the ellipse is modeled on the galaxy. Like if we add some random noise to the ellipticity or things, we can see how much that would affect the.
So what is really causing this spread is not that you introduce noise, but like you introduce like a bias in the when you do the integration.
Yeah, we're adding.
Naturally, it's complicated to call up because in the interization you go to the highest integer or you go to the nearest integer. Like if you have a number like 57.4, does it become 58 or does it become 57? And 57.6 would be 58 or?
And now you have to check the
It's in the
right, because this it becomes either a bias or in fact it is part of randomization.
Hi, great work. I have a question. When looking at the shape of this this plot, you see that I guess you've done the numbers, but the dispersion doesn't decrease extremely as you go to higher signal to noise, while in the HST data, it seems to decrease much faster.
So the thing is, in the HST, you see, we go to the even 100 is simultaneous ratio. But if you take, because we have cut it at 20 in the cases of decimation, but if you go further, you see that it becomes a straight line at some point. Just everything is
Didn't notice.
yeah, and I would like to put it on 20, but the shape was kind of odd, and the information you get from that, it wasn't really nothing, so it is better this way, even though it's not really changing the slides.
Any more questions? No? We can say, Pedro?
Summer is over.
Me pasó todo el